What's poppin', spider boys and girls? Today, we're not really gonna learn anything real new. I think we're gonna just take an opportunity since we've got a little while before that wonderful AP test that you are all looking forward to so much. That we're gonna just practice doing some stuff. Because honestly, last time I feel like the video was too much like someday you might use these equations. Uh, you better know that they exist. Let's check out some stuff that has nothing to do with any of the equations we talked about for half an hour. So, this is kind of like a supplementary equation usage day. Um, all right, never mind. I'm just gonna be honest with you. We haven't touched numbers in a while, and I just got like a craving. You know what I mean? Like we gotta number a little bit. This is my own bias. Maybe you know totally enough about rotational kinematic equations, but me personally, I feel like I don't get something unless I like dig my fingers into it and it kind of sticks between your fingernails, and you're like, ugh, how'd that get there, right? So we got to get some kinematic equations under our fingernails so that you've got more than just like a consciousness that they exist. You've got to have used them before, right? It's one thing to watch a guy use a hammer to hit a nail into a piece of wood. It's another thing to smash your own thumb open with it. So we're going to go smash our thumbs open. I only have 3 examples for you today, and one slide with all the equations on them in case you forgot to write them down the first time, and so that they're kind of all collected in one place. We're not going to spend too much time talking about them, but we're going to use the heck out of them today. So let me just double check that I've got my calculator all set and ready. Let me just press some buttons on it, make sure it revs up. Wop 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 wop. Yeah, it sounds good to me. All right, let's go learn. Okay, here are our kinematic equations for rotational junk. Remember, theta is displacement. I knew that 2 wouldn't fit. Omega is velocity. Whoops. And then alpha is acceleration. Okay. These are all the angular versions, which is kind of the fancy. I don't know. It's not even that fancy, right? It's just the word for the spinny part rather than the going in a straight line part. So, here is our displacement equation. Here is our velocity equation. There is no acceleration equation because we're not going to be changing acceleration. And if we do, we're going to completely avoid the question by using something else that probably looks at forces rather than acceleration directly. Here is your average velocity equation. If you know how far something starts, how far something stops, and then how long it took, it will tell you the average velocity. Here's average acceleration. Here is the convert between convert. How about we, instead of convert, we call them conversion. Is that how you spell that? I don't know. Conversion equation. So this is how you go from the linear stuff to the angular stuff. Okay. I'll show you how to use this stuff on the first example, I think. And then here's just some handy constants or conversion ratios to know. One full rotation is 360 degrees, which you probably know. Also 2 pi radians, which is about 6.28 radians, give or take. But here's all the like nitty gritty stuff we're gonna use, right? Here's our hammer. Here's our socket set. Here's our sandpaper. Here's the tools we're gonna use. Here they are collected in one nice place. Let's go use them. Let's quit dilly-dallying and go use them. All right. So we're gonna start simple. This is like the most classic rotational motion problem in existence. If you open a textbook to the very first page of rotational motion, there's going to be a bug crawling around your vinyl record player without fail. And if there's not, tell them you want your money back for your textbook. So what we have is a non-binary bug, very similar to a ladybug, but I figured to myself, if they're non-binary ladies people, why not bugs? So anyway, a non-binary bug. We'll figure out how to draw that in a second. Has crawled onto a vinyl record as it spins on the record player. The record is 30 centimeters in diameter and has a and the non-binary bug is 12 centimeters from the center. The vinyl record rotates at 33 RPMs, which is revolutions per minute. So a revolution is a full all the way around. What is the angular and linear distance of the non-binary bug after a 3 minute and 30-second song has played? So we want to know how far is the stinking thing going to go. So let's draw a picture so we know what we're looking at, right? We've got our vinyl here. From one edge all the way to the other, that's 30 centimeters, which means our radius, which is the probably more important physical property of a circle for these problems, is 15 centimeters total. And then our non-binary bug, let's make it maybe, what do non-binary bugs look like? This, and then we'll put like small antenna, and then instead of black spots, how about white spots? Not that there's anything wrong with black spots, but you know, for the sake of like, never mind, it's a joke. Not that I think that that's something to joke about, but anyway, so here's our situation. This non-binary bug has a radius of 12 centimeters. It's 12 centimeters from the center. Okay. So what we want to know is while this record is spinning, our non-binary bug is going to go in an ellipse. No, in a real circle. We're just looking at it angled. And we want to know what is the angular distance it travels? What is the linear distance it travels? Okay. I was very careful here to use the word distance instead of displacement. Because if this thing rotates, and let's say hypothetically the vinyl record stops where it started, right? End song, the bug is back where it started. What would be the displacement? 0, because we started where we stopped. So we're gonna look at distance. We're gonna look at like what's the full travel length path of this bug. Okay. So we want to know this displacement and we want to know this distance. Cool. So what information do we have? We know that it is 12 centimeters from the center. We also know that it rotates at 33 RPMs. This is our angular velocity. This is omega, and it's in 33 revolutions per minute. Okay, so what we could do, right, this is totally possible, is we could really easily convert this to radians per second. Or we could not. It's kind of up to us. For the sake of just practicing with radians, we should probably do that. Yeah, let's go ahead and convert this to radians per second. So we'll practice our unit conversions. Let's get this into like a more standard thing, and then we'll throw it into a equation, and then we'll call it good. So if I want this thing 33 revolutions per minute to be in radians per second, there are 2 pi. Whoops, that's in the wrong spot. Gosh dang it, you guys. I didn't think this through very well. There are 2 pi radians per 1 revolution. So going around 1 time is 2 pi in radians. Okay. For our minutes, in 1 minute, there's 60 seconds. So what we're going to do is we're going to just multiply across. So on the top, we have 33 times 2 times pi. So we could either say that this is 66 pi per 60 seconds, or we could say that this is 207.345 radians per 60 seconds. And then we could divide that by 60. And we could get 3.46 radians per second. So either one is probably fine. But let's just use this number here. Okay. So far what we have is our angular velocity in a more standard speed. And now let's get into the nitty-gritty, right? We're looking for angular displacement. Okay. We have our time. Time equals 3 minutes and 30 seconds or 210 seconds. Let's go ahead and find our angular displacement. That's the easiest. So angular displacement is equal to initial angular displacement plus omega naught times t plus 1/2 alpha times t squared. Okay. If this bug just happened to land on already spinning disk, the disk is not going to be changing speed, because if it did, your music would sound funky. So it spins the same speed the whole time. That means our angular acceleration is 0. So this term we can just throw away. That's 0. We don't really care where it starts and stops. Sure, this is probably in some kind of like nice cabinet, and there's probably like the arm thingy on here, but oh well, you know what I mean. Where it landed, that's the initial, so we'll call that 0 as well. And then we just have to plug in these two numbers, our speed and our time. So theta is equal to 3.46 radians per second times the number of seconds, 210. And then we're going to just pop that thing into our calculator. And we get theta equals 725.71 radians. Okay, this is probably almost nonsensical to you, correct? So here's what we're going to do. We're going to divide that by 2 pi just to turn it back into full. Whoops, I messed up. Let me try one more time. Answer divided by pi. Okay. What this is in rotations is 115.5. So we're going to go around 115.5 times. Okay. Either one would be fine, of course. You could write it in radians, but I feel like a lot of students don't have a really good intuitive sense of how big a radian is. So usually in rotations is a little more meaningful, but cool. So we're going to go around 115.5 times. This will be our angular displacement. Now we want to know, what is that distance? So if our bug stays at 15 centimeters, what's the linear distance? If I took its path, right, and then I like unrolled it. So this is it unrolling, right? How long is this rolled up path? So to get this linear path, what we want to use is this equation right here from the previous slide. We are going to just multiply our angular distance by our radius. So this is why you want it in radians per whatever, right? In radians, period. Because for one reason or another, radians is the only unit that really works here. So if we plug in this, theta times r equals our linear displacement. So we have 725.71 radians times our radius of 0.12 centimeters equals, grab our calculator, times 0.12. We get 87.09 meters. So this 0.12, this is in meters. So this is coming out in meters. So we're going to go 87 meters, almost a football field. So while your bug is listening to your music, it goes almost a football field in distance. Ooh. Yeah, so let's take a second. The reason we're beating this thing to death with algebra is because while it is nice to sit and just go, well, this thing doubles, so that thing doubles. Well, you know, conservation of momentum, so whatever it started with, it ends with. It's nice to be able to explain how a problem should be done. I think it's another thing to do the problem. And I feel like, you know, I'm trying to give you a balance of that. So once again, we're doing the problems with numbers because every once in a while it's nice to get numbers all over your face and like you gotta lick your fingers clean and whatnot. So there we go. So there's a ladybug going on a disc. It rotates 115 times before the song ends, and it's going to wait a second. Yeah. And it's going to what's the phrase here? Go almost a football field. Anyway. Can I show you maybe a shorter way to do this? If you're just looking straight up for the rotations. Let me find a nicer color. Okay. Let's revisit our units here. It's rotating 33 revolutions per minute for 3.5 minutes. Okay. Let's just do some simple multiplication. 33 revolutions per minute times 3.5 minutes. So first minute, 33 rotations. Second minute, 66 rotations. Third minute, 99 rotations. Half a minute, half of 33 is going to be 16.5. So 99 plus 16.5 is 115.5. Boom. And then what you could do is just times this by 2 pi, and then that would still give you your angular displacement in radians. So we kind of converted it to radians per second first, and then converted it to seconds, and then got this. If this is a little bit easier, you could keep it in revolutions per minute and minutes and find the answer, then convert to whatever units you want at the end. Whatever's easier for you, but you got options. You're big kids now. You got math options. All right, let's look at another problem. Okay, so we have a mass of m is attached to a heavy rotating disk by a very light string. The disk has a radius of 0.4 meters, and the frictional forces acting on the axle are negligible. So it's not going to be slowing down too much, but it's heavy and takes some effort to move. A group of students releases the system from rest, initial velocity is 0, with a motion detector placed under the falling box. They make a velocity versus time graph for the falling box below, find the angular acceleration of the disk and the angular displacement of the disk from 0 to 10 seconds. Okay, so here's what we have. We have a disk, its radius is 0.4 meters. Its initial angular velocity is 0 because the system starts at rest. And then we've got a box attached to it, falling, and then there is a motion detector placed underneath this. So this velocity is for the falling box. Luckily, this box is going to fall with a speed that's proportional to how fast this thing rotates. This thing can't fall faster than this thing will rotate. Does that make sense to you? Yes, Mr. Barton. Oh, really? It does? Explain it to me. I'll wait. Oh, okay. Yeah, that does make sense. So because they're attached, if this thing falls 1 meter, it has to pull 1 meter of rope out of this. And this thing is going to have to rotate so that the arc length here is 1 meter. So that's where that conversion between linear and angular stuff comes into play. Okay. So let's talk about how are we going to solve this problem. We're looking for the angular acceleration of the disk and the angular displacement of the disk from 0 to 10 seconds. Let's start with this angular acceleration. All they give us is this neat looking graph with velocity versus time for the mass here. But we can find the acceleration of this box using this graph. The acceleration is the slope of this line. So it goes -2 meters per second per 10 seconds. So this thing has an acceleration of negative point, sorry, not 0.5, negative 0.2 meters per second squared. All right, so that's just the slope of this line, which is the slope of the velocity time graph, tells us acceleration. Okay, if we want the angular acceleration of the disk, we can use A equals alpha r. So let's plug in our radius, which is 0.4, and our acceleration, which is -0.2, and we will find our acceleration. Keep in mind that this negative is just because of the graph. Because this thing is falling towards the motion detector, they're saying away from the motion detector is plus, and then towards it is negative. So this is just a directional thing. We could say that rotating this way is the positive direction. That's fine. So we have -0.2 equals alpha times 0.4. Divide by 0.4. There we go. So alpha is -0.5. Because 2/4 is a half, and then the decimals kind of work their self out. So we have -0.5 radians per second squared. And we could take or leave the minus. We could decide, do we want this way to be positive or negative? It's kind of up to us, just so long as we're consistent with it. But because this is negative, we'll just leave that negative. Keeping in mind that this is just a directional thing. Okay. Because we're choosing that to be negative, we're probably going to get a negative angular displacement, but again, fine. So we want angular displacement now. So let's look at our angular displacement equation. So theta equals theta naught plus omega naught t plus 1/2 alpha t squared. Okay. Released from rest, that means our initial velocity is 0. So this thing is 0. They don't tell us any sort of reference point for our starting position, so let's make that 0 as well. And now this simplifies really nicely to theta final equals 1/2 alpha times t squared. And we know alpha and we know t, and we can just go ahead and find it. So we have 1/2 times -1/2 times 10 squared. So we have -1/4 times 100. A fourth of 100 is 25. So theta equals -25. Whoops, that's not a 5. Theta equals -25 radians. Okay. If you divide this by 2 pi, it'll tell you the revolutions. Again, this negative is just telling us that we're rotating in the negative direction because, directions. Down is negative. We'll say that way is negative too. So There we go. We go 25 radians. What is that in rotations? It's like 4 something, I think. 25 divided by 2 times pi. Oops, just under 4. So it's 3.97 rotations. Yeah, I don't know. It's kind of fun. Cool. So there we go. So there's another one looking at some graphs, converting some more linear stuff to angular stuff, and then remembering how to use kinematics equations. So let's look at our last example, and then we'll get you guys working on some of your own problems just to really grind those numbers. So there are 2 merry-go-rounds at a park near your house. And when I say merry-go-rounds, I don't mean that you live in like Fountain Hills or Scottsdale, where just every park has like horses on poles. Not, right, not this merry-go-round. Not this one, right? That's a dog. Not that one. Okay. The merry-go-round I'm talking about is this merry-go-round. I don't know if you've ever seen these. These are pretty tight. They're just super dangerous. So they don't really have them anymore. But basically, it's just a rotating disc with some bars that you can hang on to. So we've got 2 of those. One with a radius of r and one with a radius of 1.5r. So it's 50% bigger. You sit on a merry-go-round and you have your friends spin you as fast as they can. When you're spinning on the smaller merry-go-round, it takes 1.2 seconds to make a full rotation. So going all the way around is going to take you 1.2 seconds. When you're on the larger merry-go-round, it takes you 1.6 seconds to make a full rotation. In which case do you have the larger translational velocity? So we've got 2 merry-go-rounds. One's a little bigger than the other. We know their radii, and we know their time to go in a full circle. So let's try and figure out which one's going faster. And when we say translational velocity, we're talking about like here you are hanging over the rail. How fast that way are you going? What's your linear velocity? So if we want to know this, let's look at a couple of things. Obviously, this one takes more time, but you're going in a bigger circle. So what omega is it's the total rotation divided by change in theta over change in time. Okay, so let's find omega first. In both cases, our full angular displacement is 2 pi. You go in a full circle in both of these. So you have 2 pi divided by 1.2 for this one. And then our omega for this one is 2 pi divided by 1.6. Okay. Obviously, this one, the smaller one, has a larger angular velocity because it takes you less time to go in a full circle. But because the circle we're going in is smaller, maybe we don't have a larger linear velocity. So now what we're going to do is we're going to take this and convert it to a linear velocity using v equals omega r. So we're just going to multiply this by r. So the r here is just r. So we have v1 equals 2 pi r over 1.2. And then over here, our radius is 1.5 r. Okay, so v2 equals 1.5 r times 2 pi over 1.6 multiplying 1.5 times 2, we get 3 pi r over 1.6. So both of these have pi r in the top. So we don't really care about that part. What we care about is what's bigger, 2 over 1.2 or 3 over 1.6. So whichever coefficient is bigger will tell us. So we'll grab our calculator, just reduce these fractions real quick. So we have 2 divided by 1.2. That's 1.6 repeating for our coefficient. Then we'll do 3 divided by 1.6. That's 1.875. So because this one has a bigger leading coefficient, we would say that this one has a larger velocity. So even though we're spinning in a circle slower, because the second merry-go-round is bigger, the length of the circle makes up for it, and you're actually traveling faster here. So this one has been a little bit of just brute force. Let's mash our faces into some numbers, but I think sometimes we miss out on that. I miss it. I like just bashing into numbers. I think it's fun. So hopefully you kind of learned something. I hope I didn't kind of hand wave everything too much. If you get stuck on your homework, let me know, and then I'll help you. I'll help you set up the problems. But until then, have a wonderful rest of your day, and good luck on your homework.